Okay, so here's our quandary. Did you guys did anybody get like 59 point something for the velocity afterwards? Did anybody get that? Okay, so here is, shut up, here is, be quiet, thank you. Okay, the bullet is flying along, right? And the block is sitting still in the first picture, so here it is. The block is now frightened, right? It's like, yeah, right? That makes me feel bad. I better erase that. Okay, so there the bullet is, right? In the after picture, it is that the bullet is stuck into the block, and the two of them are now moving along, right? So this is 0.1 times 560, isn't it? Right? Yeah. And then that equals, and then this is the bullet and the block are 0.945. Right? So I added, yeah, well, it doesn't matter. You actually keep them all in grams and still get the right velocity. I'm just doing it now because if you do joules, if you try to get energy, 1 FmV squared, you'll be wrong when you do that. And then this is times the unknown velocity, yeah? Yeah. So go ahead and take your calculator and calculate what that V is. I'll do the same thing if you didn't do it. Yeah, I know. It's like, when you think about it. Okay, so 0.1 times 560 divided by point. Okay, now this is a crazy thing. The velocity ends up being 59.259, and then shut up. Shh. Only I get to talk about winter break or spring break. Wait, did I just lose a few months? Okay, I love repeating numbers. And this one's like 259, 259, 259, isn't it? Yeah, that's just crazy. Well, because, it's got to stop at some point, right? Okay, so there's our velocity. I'm going to actually take that number because a very strange thing happens if you use that exact number when you calculate the kinetic energy. So I'm going to take that, I'm going to go storage, and then I'm going to go alpha A. I'm storing that number in there. Now, the kinetic energy, that's our velocity, okay? Now let's figure out the kinetic energy. Did that end up being the same? Did anybody calculate it? Is it the same before and after? Let's all calculate it. Everybody get a calculator out, and by touching your calculator, get these answers. So the kinetic energy before is 1/2 0.1 560 squared, right? And the kinetic energy afterwards is 1/2 945 0.945, right? Okay, times, and then you got to use this number 59.259. 259, 259, 259, 259, 259, 259, 259. Oops, oh sorry. I told you they're kind of crazy, right? Okay, squared. So calculate both of those. Calculate this, calculate that. The question is, are they the same? Can a smaller mass moving faster have the same kinetic energy as a larger mass moving slower? They could, but do these have...
Where did the 945 come from?
That is going to be the 0.1 sticking in the 0.845, yeah? Does that make sense? Together they are 0.945, huh? Okay, so squared times 0.945. Okay, now, this is just freaking me out. Because this answer on this side here, if you don't round that thing, right, is 1659.259.259. Yeah, look at that. Isn't that a little freaky? We've discovered something here. There's something hidden in these numbers. I don't know. Okay, so this is joules, right? And if you do this one, we get a lot bigger number, don't we? 0.1 times 0.5 times 560 squared. This is 15,680. Okay, now, is it true that the kinetic energy before the collision is the same as the kinetic energy after the collision? No. Which one is more? Way a whole lot more. Now, I thought energy was conserved. This is, by the way, a talk radio show hosts do this, right? This is a diversion. I thought energy was conserved. Didn't we spend a long time teaching that energy is conserved? Well, I thought it was conserved. It's not conserved. Look, right there. Let's move on to the next topic. No critical thinking needed. Yes? I thought energy was conserved. Here it's proof that it's not. This is like 1/10 of that. Yeah? Let's go on to the next topic. No critical thought. Yeah? Energy is conserved. Yes. Is kinetic energy conserved? Not necessarily, because kinetic energy can become potential energy, or in this case, probably some of that kinetic energy turned into heat. There we go. That's our favorite word. Yes. Okay. Bullets, when they hit solid objects, lead bullets melt. Okay. One of the things that forensic scientists look for is little spatters of molten lead from the collision. Lead has a pretty low melting point. You can melt it over a candle flame. Okay. So, yeah. Oh yeah. Yeah. It's really low melting point, right? So it's got such a low melting point that it actually melts on these collisions, right? So the fact in this collision that roughly 9/10 of this kinetic energy was turned into heat, that makes this an inelastic collision. Inelastic means not elastic. Inelastic means bouncy. Okay, so that's where we're headed today. We're going to talk about elastic and inelastic collisions. We got crazy demos, and yeah, there we go. Right? So let's look at an elastic collision. Let's look at unelastic collision. Yeah, I'd take some notes. You better take notes. Everything I say is vastly important. Okay? And I like these guys. These are my favorite guys here. Let's turn this on. Okay. Here is an elastic collision. Watch this. Ta-da. Whoa, I love that. Isn't that fun? What do I have on there? Yeah. Freaking magnets. How do they work? Have anybody ever seen that Insane Clown Posse Miracles? I'm paraphrasing a little. They don't actually say freaking magnets. They say something else. Okay. But yeah, this is an elastic collision. And elastic collisions have, whoops, that was inelastic there for a moment, because some of the energy was turned into sound. We heard it go clank, right? But if it truly turns the kinetic energy before and after, if that's truly the same, then you don't hear clank. It's not making heat. It's doing that. This is what we mean by bouncy. Okay? So let's hit the right arrow here, see what it says. Kinetic energy is conserved. So in an elastic, a fully elastic collision, the kinetic energy before equals the kinetic energy after. Is that always good? Like in a car crash? Do we want to have the kinetic energy be the same before and after the crash? No. Do we want to have the car run into a big spring on the side of the road and get flung back into traffic going the other way at the same speed? No. Yeah, generally we try to avoid that, don't we? In fact, what do we put in the path of traffic? We don't put big springs. We put those barriers, and what's in those barriers? Water. Yeah, water or sand or something, right, that makes the car just go mush, yeah, and stop. The car stops. We want to stop the car. How about those barriers? Those barriers that separate the lanes of traffic. Have you ever noticed that they're wider at the bottom? That's so when cars hit them, the rubber of the tires hits them and the cars slow down. They're trying to get rid of kinetic energy. So generally in collisions with cars, we want to get rid of collisions. Elasticity is not really what we're after. Okay? Okay. A spring bumper on a car is elastic. Molecules are elastic. So like in an ideal gas, when ideal gas particles collide with the wall of the container, right? It's the electron clouds overlapping with the other electron clouds. They just kind of go boom like this. It's like this, only it's not magnets. It's an electrical repulsion. Yeah, that's kind of fun. Isn't that fun? All right. And then here is a crazy thing about elastic collisions. Just, I don't know if this is useful for you, but elastic collisions are reversible. If you undergo an elastic collision with your car, you don't have to tell your parents afterwards. Okay? In other words, your car looks the same before and after the collision. Watch this one, though. The collision itself could be played backwards and you wouldn't know. Here's collision number 1. Ta-da! Here's collision number 2. Ta-da! Aren't they exactly the reverse of each other? Yeah, every collision, you could film it forward, you could film it backward, right? I could drop the film, as in an actual piece of plastic, on the ground, pick it up the wrong end, feed it into the projector, and you wouldn't know which way you're seeing it, yeah? Think about an inelastic collision, like the bullet hitting that block of wood. If you saw the reverse of that, you might know something's going on.